Good afternoon to all. I am Dr. Dhondiba, Assistant Professor of Chemistry, Government First Grade College, Kerpuram, Bangalore. Today I am going to discuss fourth session of Chemical Kinetics, which belong to third semester BSc, affiliated to Bangalore North University. In this session, I have to discuss about determination of order of a reaction by different method and what is the effect of temperature on the rate of the reaction. These I have to discuss in this session. Now, what are the objectives of this session? The first objectives of this session is goes to determination of order of the reaction by different methods. There are four methods are there that you have to discuss one by one. Second one is effect of temperature on the rate of the reaction, and third one is explanation of probable distribution curve of effective collision. These we have to study in this session. Now, after completion of this session, you come to know about how to determine that is the order of the reaction by different methods, and also you come to know about effect of temperature on the rate of the reaction. Again, you also can be defined as easily temperature coefficient, and what is the probable distribution of curve, or what nature of the probable distribution curve that come to known after this session. Now, before this commencement of this session, you have already know about rate of the reaction, then law of mass action, then rate of the reaction depends on the temperature also. You already know about these concept. By using these concept, you have to study few more concept in this session. Then coming to that is a determination of order of the reaction. The what is mean by order of the reaction? The sum of the powers of the concentration terms of a reactants in the rate equation is called order of the reaction. The simple you say that sum of the powers of the concentration terms found in the experimentally rate determined equation is called order of the reaction. Order of the reaction may be zero or fraction, or that is a negative or whole number. Okay. Order of the reaction can be determined by using following methods. First method goes to differential method. Second method is goes to integration. Third method goes to that is half-life period, and fourth method is goes to isolation method. These are the methods to determine that is the order of the reaction. Now, first we have to study one by one. First one is determination of order of the reaction by differential method. This method is also called as a want of differential method. For that, consider a rate of reaction of nth order reaction is given by minus dc divided by dt equal to k into c to the power of n. Applying the log on both sides to this equation, you will get log of minus dc divided by dt equal to log, that is r, it is a rate, equal to here actually that is on log of k into c to the power of n. Again, we know that by logarithmic property, the product of the two, that is log m into n property, therefore log k plus log c to the power of n. Again, m to the power of k property will be there, therefore we can write that is a log of that is n into log c. Therefore we can simply, by applying that is a logarithmic property and logarithm to this equation, we can write that is finally negative, that is a log of minus dc means change in concentration in time dt equal to, that is r is nothing but rate usually, therefore minus dc divided by dt log r is equal to log k. K is nothing but rate constant, and n is nothing but order of the reaction, and c is nothing but concentration. Okay, therefore we can write that is a log k plus n into log c. Call equation number 2. Plot the graph of log of minus dc divided by dt against log c For the above equation, it gives that is straight line curve with the intersection of y, with intersect the y. The intersection of the y axis, no, that will be gives that is a log k value, log k value. Now here intersection of k, it is the slope of the curves in order of the reaction. Therefore we get that is a, after that is plotting the log r, that is the log minus dc divided by dt on x y axis and log c on x axis. We will get that is a intercept at this, and this gives, you know, this is the log k, this is the logarithm of rate constant, and slope of the curve we can draw or we can find by plotting right angle triangle on this curve. Therefore we are right angle triangle means a b c, therefore it became a theta. Therefore change in that is a tan theta, or it is also called as slope of the curve, is nothing but bc, change in y axis, that is a bc divided by change in x means dx or ab. AB you have to change, you have to extrapolating this we will get that is a we will get dx value or AB value, and here BC value extrapolating to the y axis we will get that is the value. Therefore slope is equal to BC divided by AB, and that is equal to, you will get that is a n is nothing but order of the reaction. The two experiments of the two rates of above equations with the two initial concentrations C1 and C2 in equation 1 are given by, we have to we have to experimentally determine. How it is experimentally determined? Letting the concentration of the C1 is the concentration of the one reactant in one experiment, and C2 be the another concentration, initial concentration of in another experiment. Then to follow we will get that is a change in concentration of C1 is nothing but minus dC1 divided by dt is equal to kC1 to the power of n. This is called equation number 3. And similarly, so another experiment you have to carry it out by taking the initial concentration C2. Therefore we will get that is a negative sign of dC2 divided by dt is equal to k into C2 to the power of n. It is called equation number 4. Now divide equation 3 by 4. What you get now? After dividing the 3 by 2, we can write that is a minus dC1 divided by dt whole divided by minus dC2 divided by dt. We can also simply we can write that is a minus dC divided by dt. It is represented as rate 1, that is R1, and d minus dC2 divided by dt, this can be represented as R2. Therefore R1 divided by R2, this is equal to, we can write that is a kC1 to the power of n divided by kC to the power of n. Then here this k get cancelled. Then we have to make R1 divided by R2 equal to C1 to the power of n divided by C to the power of n. Again you have to make, this is the common power. Therefore R1 divided by R2 equal to C1 divided by C2 to the whole to the power of n. And taking the logarithm side, logarithms on both side, what you get? That is log of R1 divided by R2 equal to log of C1 to the power of n divided by C2 to the power of n. This is making the there only, or here you can be making the common power here. Therefore we can write that is a log of R1 divided by R2 log of C1 divided by C2 to the whole power of the n. Then again logarithmic property you can write that is here log R1 minus log R2 equal to n log of, again that is a m by n property, log C1 divided minus log C2. Then you have to find out the value of n. Therefore n is equal to, transfer this value that side. Therefore we will get that for n is equal to log of R1 minus log of R2 divided by log of C1 minus log of C2. And this equation gives that is a experimental that is a order of the reaction, where n is nothing but order of the reaction. This equation gives the useful to determine that is a order of the reaction by differential method. Okay. Now coming to that is second method is nothing but determination of order of a reaction by methods of integration. This method is also called as a trial and error method. Trial and error method, because we cannot be get that is the answer. If it is, you have to first try, make the trial. If it is correct one, you have to keep. If it is the wrong one, you have to go to other. Therefore, this method is a trial and error method involving the use of different rate equations. The rate equation which gives the constant value of K corresponding to correct order of the reaction. In this method, the different initial concentration of reactants A are taken, and the concentration left A minus X after regular interval of times are measured. These values are substituted in the following equation. Therefore, simple here. First, you have to let the reaction, it is having an initial concentration, and X be the change in concentration in time t. After time t, certain time t, A minus X will be a remaining left over the concentration in interval of time. Then substitute these values in following equation. For a zero order reaction, suppose K, for zero order reaction, K is nothing but K is equal to X by T. You have to keeping the X value in different interval of time. If it is getting constant value, suppose calculating two or more trials, two or more, that is trials, we will get that is the same value. We are getting that is a K value is constant from experimental data. Then the given reaction should be a order of the given reaction is zero order. If it is not constant, then we say that is it is come to know that the given reaction is not a constant. Then go to that is again you have to choose the other, that is rate constant of a first order reaction. First order reaction, that is nothing but K into 2.303 divided by T log of A divided by A minus X. Now substitute this value, initial concentration, A minus X value, and T value, the different interval of time, that is a 5, 10, 15, whatever maybe, 1, 2, 3 trials you have to do. If with value is getting, that is K is equal to constant value after different interval of time and change in the concentration, we will get that is the same value. Then we know that we conclude that the given reaction is nothing but first order reaction. If it is not constant, then go to choose the next another, that is the equation for second order reaction. For a second order reaction, K is equal to 1 divided by T into X divided by A minus A into A minus X. This is the expression will be there. Then you have to substitute the value of X, A minus X, and A and T in this equation. Again, for different interval of time, you are getting that is a K is constant for 2 or 3 trials. Then we conclude that that given equation, given reaction is nothing but second order reaction. Otherwise, if it is different to different trials, then it is say that is it is not a second order reaction. Then you have to choose that is for third order reaction. Third order reaction, no, the K is equal to X into 2A minus X divided by T into 2A square into A minus X. Now substitute these values X and A and T in this equation for different interval of time. Again we are suppose getting that is constant value for 2, 3 trials. Then we say that is conclude that the given equation is, that is order of the reaction is third. Therefore, among these one will be a matches, and from that we can calculate that is a order of the reaction. This method is called as a integration method. Now come to that is the third method, determination of order of the reaction by methods of half-life period. We know that for that now we know that the relation between the order n and half-life period of a reaction given by T half is equal to 1 divided by A to the power of 1, n minus 1. The T half is directly proportional, inversely proportional to 1 divided by A to the power of n minus 1, where A is nothing but initial concentration of the reaction. Let the initial concentration of the particular reactant be A1, and another one is A2 in a two different experiments. You have to carry it out for that two different experiments in which the initial concentration of one experiment is let A1 and another one in another experiment you have to let A2 be the initial concentration, and then corresponding half-life period, half-life change or half-life period of each experiment you have to calculate. That will be denoted as T half 1 and T half 2 respectively. T half 1 for experiment number 1 when the initial concentration is taken as a A1, and T half 2 is the half-life period of a second experiment in which A2 is the initial concentration respectively. Then we will get that is the two equations from this. T half 1 is that is inversely proportional to 1 divided by a to the power of n minus 1. This is the 1. This is called equation number 2. Similarly, T half is proportional to 1 divided by a to the power of n minus 1, that is the 2. That is called equation number 3. Now divide equation 2 by 3. What you get after dividing? Therefore T half 1, T half of 2 equal to a to the power of n minus 1 2 divided by a to the power of n minus 1 of 1. Then we have to make that is common, the power is n minus 1. Therefore we can write that is the T half of 1 divided by T half of 2 equal to a2 divided by a1 whole to the power of n minus 1. Taking logarithms on both sides to the above equation, then you will get that is the log of T half 1 divided by T half 2 equal to, then you have to apply that is the logarithm, no, logarithm m to the power of k means n minus 1. Therefore n minus 1 log of a2 divided by a1. Again you have to apply that is a logarithmic property. Now divide, no, therefore it is the subtraction will be takes place. Log T half 1 minus log T half 2 equal to n minus 1 into log of a2 minus log of a1, close the bracket. Therefore n is equal to 1 plus log of T half 1 minus log of T half 2 divided by log a2 minus log of a1. This equation gives that is a order of the reaction, by half-life period. Now coming to that is the fourth method, that is the determination of order of the reaction by isolation method. This is the most important part, examination point. This method is also known as Ostwald's isolation method. This method is particularly suited where two or more reactants are involved. This is the isolation, means picking. Already there, the order of the reaction you have to pick there. Therefore this is the Ostwald's isolation method, in which it contains that is a more than two reactants should be involved. Two or more reactants should be involved, then only this method is applicable. The order with respect to one of the reactant is determined. The order with respect to one of the reactant is determined by keeping the concentration of all reactants in large excess except one reactant. The reactant is not taken in excess is isolated. The order is determined with respect to that isolated reactant. Now here this means, suppose A plus B plus C will be that is more than two reactants are there involved, then you have to take only one reactant is sufficient quantity and other reactants are taken large excess. Therefore due to having a large excess, the concentration change, no, that is in the reaction is negligible. That should be a negligible, like a pseudo unimolecular reaction. Suppose hydrolysis of methyl acetate, no, hydrolysis of methyl acetate. Here water and methyl acetate is take here two molecules, but it is the rate will be depends on order of the reaction depends on only that is a concentration of methyl acetate, because water is taken in large excess, and that will be neglected. Therefore here two or three reactants are there, no, for that one you have to take, that is a sufficient quantity, measurable quantity, and other reactants are taken in large excess, and that corresponding changes in the rate of the reaction, that you have to neglect it. And we have to, what you have to taken as a measurable quantity, yeah, with that reactant respect to, you have to calculate the rate or order of the reaction, that will be isolated. Therefore we say that is the order with respect to one of the reactant is measured by keeping the concentration of all reactants in excess except one reactant. Except one reactant, other concentration of the reactant will be taken as a large excess. Okay. Therefore the rate and order of the reaction that respect to that reactants will be a negligible. The rate the reactant is not taken in excess is isolated, and the order of the reaction with respect to that isolated reactant is calculated. For example, consider a reaction of the type, just I take that is a, for example, consider the reaction of the type A small a be the initial concentration of the A, and B be the initial concentration of the reactant B, and small c be the initial concentration of the reactant C, and small d be the initial concentration of the reactant D, and to formation of the products. Now here first you have to carry it out. You take that is a mole per dm cube. It is you take that is 1 mole per, a is nothing but 1 mole per dm cube, and these others are no, c b c d, these reactants are taken as a large excess. Therefore the rate, that is order of the reaction, you have to depends on only that is the a concentration, that is the a reactant, and you have to isolate that one. And similarly next experiment you have to carry it out. You have to take that is B is the 1 mole per dm cube, and A, C, D are, these are the reactant are in large excess concentration, and therefore the rate will be a negligible, and therefore order of the reaction is only, that is concerned to measure with the respect to B concentration, that is taken as a B1. And third one similarly you have to in third experiment, third trial, you have to calculate the concentration of A, B and D are taken in large excess, and concentration of the reactant A will be isolated, and you have to find the order of the reaction with respect to, that is a C. Therefore it is considered as a C. And last one is last experiment, the D is taken as a measurable and others are taken as a large excess, and therefore you have to take that is isolate or measure that is the order of the reaction with respect to D only. Then the overall writer, then we say that is I told that is this much, no, for that I have to read here. The order with respect to A is measured by keeping the concentration of B, C, D in large excess. The same process is repeated with regard to the other reactants also, and the other order with respect to the B, C and D determined. If the order with respect to the A, B, C and D are A, B, C and D respectively, then total order of the whole reaction is equal to, n is equal to, you have to take that is sum of the order of the each concentration in each experiment, that is A plus B plus C plus D, and this method is called, that is a isolation method for determination of order of the reaction. Now next coming to that is the effect of temperature on rate of the reaction. We know that as the temperature increases, the rate of the reaction increases. Why it is a rate of the temperature increase? Why? By increasing in temperature, the rate of the reaction increases. Here we know that as the temperature increases, the rate of the reaction also increases. It is expressed in terms of temperature coefficient. It has been found in experimentally for a chemical reaction with rise in temperature by 10 degree Celsius, the rate of the rate constant is nearly doubled. A rate constant will be a nearly doubled when the every 10 degree rise in temperature. The temperature, therefore, the temperature coefficient of the reaction is defined as the ratio of rate constant at two temperatures. The rate constant, ratio of rate constants at two different temperatures differing by 10 degree Kelvin or 10 degree Celsius. Generally, that is a 25 degrees Celsius and 35 degrees Celsius. This is the differ in 10 degrees Celsius temperature. The rate of the reaction will be almost double, double or triple. And this is called as a temperature coefficient. Temperature coefficient is equal to K2 divided by rate constant of two different temperature. The lower temperature here and higher temperature. It is taken as a rate constant, that is a 25 degrees Celsius temperature, and rate constant is 35 degrees Celsius. Therefore, rise in temperature, 10 degree rise in temperature or 10 Kelvin temperature rise in, it gives that is the rate of the reaction between 2 to 3, or rate of the reaction almost all double. This is called as a temperature coefficient. Therefore, this is the important for 2 marks. The question will be asked, define temperature coefficient means the ratio of rate constant at two different temperatures differing by 10 degree Kelvin temperature or that is 10 Kelvin temperature. The rate of the reaction is almost all doubled or tripled, called that is a rate coefficient of temperature coefficient, called temperature coefficient. And mathematically we can write temperature coefficient is nothing but KT1 T plus 10 divided by KT equal to, that is nearly 2 to 3, that is 2 or 3, that is it is made up, that is a rate of the reaction double or tripled. Now in the last one, it is we have to explain about why the 10 degree rise in temperature, the rate of the reaction almost all double. That can be explained by using probability distribution curve of effective molecules with rise in temperature 10 degree. As we know that rate of the reaction is doubled or tripled by rising the temperature 10 degree. This can be explained on the basis of probability distribution curve. As the temperature increases from T1 to T2, the energy of distribution undergoes a change as shown in figure. There is a general shift in distribution of energies as shown in figure. Now how it is, the most probable molecules will be there in the lower temperature here. As temperature, the effective, as the temperature increases, the degree of effective collisions increase, that is the main, that is the effective collision numbers increase, hence the rate of the reaction also increases. The Maxwell-Boltzmann equation now here, this is the hip of, that is a curve will be there. This is the Maxwell-Boltzmann probability curve in which the molecules are taking participate. At that is T1 temperature, the molecules will be possesses this type of the curve and the area will be this like. Therefore, suppose we are taken here the molecules here. But when we are rising the temperature, as the temperature rises, the kinetic energy rises. The number of molecules whose energies are equal or greater to the threshold energy at T2 temperature is represented as shaded. Therefore, we say that is the number of molecules whose energies are equal or greater than the threshold energy at the temperature T1. This is the represented as shaded line. This is and at the T2 temperature by shaded, that is area, that is this is the A, B, C, D. This is the shaded area of temperature here T1. Here in which the molecules are less molecules are there, it is the effective collisions are takes place. But when it is equal to, that is a threshold energy, equal to or greater than threshold energy, and hence it gives, that is the rate of the reaction. As the temperature increases, that is the T2 from 10 degree rise in temperature, that is the T2, this area will be again, that is doubles. Double means the molecular collision, that is probability of the finding of the molecules will be a double, almost all double. Therefore rate of the reaction also double. Therefore the shaded that is area, that is A, B, EF, this is the concern to about, that is a T2 temperature, because the 10-degree rise in temperature, the almost all that is molecules are double, and therefore rate of the reaction will almost all double. This is means that is the number of molecules having energy equal or greater than the threshold energy becomes nearly double even with small increase in range in temperature from T1 to T2. Consequently, the rate of the reaction, which depends upon the number of effective collisions, the becomes almost all double with small increase in rise in temperature. As discussed above, there is a certain minimum energy, threshold energy, which colliding molecules must acquire before they capable of the reacting. This means as 10-degree rise in temperature, the effective number of collisions almost all double of earlier. That is it is increases as the number of effective collisions are double, then rate of the reaction almost all double. Therefore as the temperature increases, the number of molecules in probability boards probability molecular that is area will be increases, hence the rate of the reaction almost all double. So far we have studied in this again we say that is here the most, however this much lesser, and the energy of the threshold energy, the excess energy that molecule have a less threshold must acquire, that is a product yield as a activation energy. Therefore we have say that is a this energy about the molecule. Therefore activation energy, sum of the activation, the threshold energy is nothing but sum of the activation energy plus normal energy, that gives, that is the activation energy, that is the threshold energy. And activation energy is nothing but the subtraction of normal energy from activation energy is called from threshold energy is called, that is activation energy. And so far we have studied about that is a determination of order of the reaction by differential method, determination of order of the reaction by methods of integration. Then third one is determination of the order of the reaction by half-life period method, and determination of order of the reaction by isolation method. These we have studied so far for determination of order of the reaction by different methods, using different methods. And next one is we have also studied so far rate depends on temperature. As the temperature increases, the rate of the reaction, and it is almost all doubled, and it is expressed in terms of temperature coefficient. Again the probability molecular distribution curve we can explain. At lower temperature the molecules know they are present, no occupied. Rise in 10-degree rise in temperature, the occupation of molecular probability is almost all double, hence the rate of the reaction are double. This so far we have studied. Now I have to ask some questions regarding this session. Please answer them. Then first question goes to, that is a determination of the order of the reaction by differential method is given by, who is given, that is a determination of the order reaction by differential method. First one is Arrhenius. A option is Arrhenius, B is nothing but Newton, third one is Van 't Hoff, and fourth one is none of these. I will give, that is 10 seconds for you people. You have to answer, you have to choose the correct answer. C answer is the correct answer, because Van 't Hoff he's explain the determination of order of the reaction by differential method. Therefore Van 't Hoff, that is C option, is the correct answer for this question. Second question, determination of the order of the reaction by isolation method is given by, first option Ostwald, second one is Arrhenius, third one is Van 't Hoff, and fourth one is none of these. I will give, that is 10 seconds for you people. You have to choose the correct answer. Now A option is the correct for this question. That is the Ostwald is given, that is he described the determination of the order of the reaction by isolation method. Third question, every 10-degree rise in temperature, the rate of the reaction becomes A answer almost 2 times greater, almost same, almost 2 times lesser, and none of these. These are the four options are there. You have to answer the correct answer. I will give, that is a 10 seconds. The A option is the correct answer for this question. Almost all 2 times greater. It is the rate of the reaction is doubled in every 10-degree rise in temperature. Therefore, almost 2 times greater than that rate of the reaction. This answer is correct for this question. Fourth question, expression of zero order reaction. A option, K is equal to A by T. B option, K is equal to X into T. C is equal to K into X by T. Then D is equal to none of these. I will give, that is a 10 seconds for you people. You have to choose the correct answer. Now C option is correct answer for this question. Therefore, expression for zero order reaction is equal to K is equal to X by T. This is the correct answer. And I made these references for preparation of this session. Thank you.